Before continuing the next lecture, our next lecture will be about the color image uh, and doing some activity on the color image one. Because as you know, all what we work, it was in the grayscale or on the RGB, on the two color, means that black and white colors. Picture means binary pictures. We work on these two type, and the color one is remain, which we will start in the next lecture. It's a little bit semi review on the filtering in the frequency domain, but review with the aim of Matlab codes that we have. And the main purpose of today is that beyond that, we are review the frequency domain concepts and its related topic. Mainly, I want to review about the MATLAB's code which we had about the filtering job in this frequency domain, and then the next one, the next new week, we will talk about color image part. Before continuing that, if you have any question, you can ask me. Otherwise, I'm going to start today's lecture. Any question about previous lectures?
No, sir.
Okay. Okay, let us start then. For today, we have review and code on filtering, especially in this domain. Most of the PPT part, not code part, I took from some lecture from Dr. Lin Zhang from Tongji University in China. Some point was nice that I use some of his PPT. Then to make it legal, I put his name here. But beyond his PPT, I also written some codes to make it more understandable. Is that the part that he had? First, we are going to talk about background of the frequency domain. Then we'll talk about Fourier transform and Fourier series. Then we talk about properties of the uh, Fourier transform. Then we talk about the discrete Fourier transform, basic of the filtering in frequency domain, image smooth using the frequency domain, and image sharpening using the frequency domain filters. Mainly, I'm looking for review the concepts of Fourier in whole today lecture, and also show you some results on the image, and then we'll discuss what should be the uh, effect of this filtering on the image. First, let us see the background. You know that Fourier analysis or Fourier series and transforms. It's using in many engineering fields. Even if you remember in our math book, math subject also, we use it for analyzing, but mainly these topics we'll use for analyzing the signals. And if we say signal, we have two. It can be any type of signals. It can be a speech signal, or it can be image signal, or image exactly. Linear image filtering can perform in the frequency domain, and a working knowledge of the Fourier analysis can help us to have through the understanding the image filtering. Um, Let me give you some short history that this was invented by the Joseph Fourier in 1768 in France, and most famous of his work was some uh, French name that La Théorie Intégrale, I don't know, de la Chaleur, something like that, which will be published in English. And the translation of that is the analytic theory of heat. Okay, I didn't read it proper because that was in French word, but the English meaning of that is analytic theory of the heat, which published. And by this analysis, then they put the equation with the name of his work, means that Fourier job. For any periodic function of ft, how to extract the components of f at some specific frequency is our question. Remember or assume the first waveform that I showed. If I want to extract the components in some specific frequency, suppose 1 kilohertz or 2 kilohertz or 3 kilohertz, what should I do? Because you know that any wave is a combination or composed of some other wave. So, suppose see this upper image or upper wave is combination of these three waves, which now if we want to just have the sine wave, what we should do, or this small wave or any of them, means that the summation between these three causes the first one waveform. And as you can see uh, at the top, the waveforms of signal that we have at the top. For any periodic function of ft, how to extract the components? As I said, this is uh, the question that we have. But in this image, I try to give you some view. One is that the view from the frequency domain, which can be like this from this yellow part. Or another view can be the um, idea or perspective from the time domain. You know that any wave can be between time or it can be between the frequency. What's the relation between time and frequency? Also, you already study in the physics, then no need to uh, speak about it. But having the view from the time or having the view from the frequency, it's the um, key of analysis of any wave. Generally, what we learn is that we learn to analyze the waveform in the time, but when we come to the frequency domain, there are more, we can say, data that we can extract from a waveform. Then for any periodic, we can say that the combination of frequencies can causes the waveform. And suppose if I want to have the chart, I mean the bar for this specific waveform, we can say that we have something like this. The shape is not important. Something which is more important is here that the summation is from frequency number 0, then multiply by 2, and second frequency. Then we have three type of the waveform frequency, which they are combined together and causes this white one. Okay. Then the key to analyze and extract the components is Fourier series, which any periodic function can be expressed as a sum of the sine and cosine of different frequencies, each multiplied by the different coefficient. Here, there is the Fourier series that you can see ft is equal to a0 divided by 2, and then the accumulation of the accommodation between n equal to 1 to infinity of an cosine n omega t plus bn sine n omega t. This form we call it Fourier series. Then, if we assume the ft as the periodic function and t as the period of the Fourier series, we can have the mentioned formula that I said, and we have two things. One is that omega, which is equal to 2 pi divided by t, and another one is the redundant sentence that we call it a0. Okay, and till an we have, which has the formula as I shown here, and we have one terms that we call it bn. These are the math part, but somehow I will not go more deeply for that part. But what should be if the ft, I mean the function that I have, is not periodic? If it's not periodic, we can show it with the below formula of f of mu between minus infinity to plus of function multiplied by exp of the uh, minus j 2 pi mu t in dt. And then if we take the inverse of that, inverse Fourier transform of that, we can have this. But how to get this formula? This is the question. Let us go for the math side, that as we know, e power by j theta is equal to cosine of theta plus j sine theta. Then we can written the sine and cosine with this form, I mean with the exponential form, and then somehow we can change the Fourier series with this new formula that we find from the earlier formula, and then this can come out. Okay, then again, according to this earlier formula, we can say that if we do the change on the Fourier series that we have, we can come to have the C0 plus accommodation of n plus n equal to 1 to infinity, and then we can have two parameter of Cn and Dn. Then how to calculate the C0, Cn, and Dn? It's based on the integration that we can take, and then what we can see that the C is equal to Cn minus, Dn is equal to Cn minus, and finally we can have the Fourier series in the complex form as we can have in this formula. But again, one question will remain, that what we should do about non-periodic function. Today I'm not going to go deeply in the math side because you already read these parts. Just we want to review the concepts. Okay. Then if ft is some non-periodic function, we make the new function, which we call it periodic, as the term of t. And then we know that ft is equal to ft, ft of t is equal to ft if t is between minus t divided by 2 and t minus t divided by 2 to 2d t divided by 2. These two is the domain of working of t. And then according to the Fourier series, we can have this formula, which in that we can take the limit between them and reach this result as the out. And then finally, we can say that based on taking a limit of this Fourier transform, we can remove this part and put it as Fs, which is the Fourier transform, And then if we take the integration of that, we can call it inverse Fourier transform. Then what we have caps of fs, which is equal to minus infinity to plus ft multiplied by e power by minus js dt. And if I take the integration of that with the 1 divided by 2, then we can say that this is the inverse one. As we know here, S is some angular frequency. What we learned that in the signal processing domain, we usually use another form by substituting S by where frequency measured in the hertz, and then this S can come out, and we can have f of mu like this and f of t. Then we can say that Fourier transform of f mu is complex in general, and it can be f of mu between two terms of real and imaginary part, which in polar it can be expressed as the spectrum and phase angle. This is something that we need today, some concept that we need, which is abs of f mu. It's equal to real parts and imaginary parts uh, root square by 2, which any of them is power by 2. And phase angle is the a tan of a mu divided by r mu, which if we want to calculate the power spectrum, we can have the p of mu and have this equation. These parts inside, they call it power spectrum. Then what we need three words. One is that Fourier spectrum, phase angle, and power spectrum now from the Fourier transform. But in Matlab, how we can do that? In Matlab, we have three functions to do the DFT as the Fourier transform, or the secret Fourier transform, which is not for the uh, continuous or periodic function. We know the FFT is for one dimension, it's useful. FFT2 is for the two dimension, which is useful for the image. And FFTN, it's good for the n dimension. And we have three related functions as IFFT, IFFT2, and IFFTN. Then what we should learn is that because we work with the image one, then FFT2, which is for the image, and as we know, image has two dimensions of x and y. In MATLAB, we should use this FFT2. Then let us see. Uh, in the suppose if I want to make one if I want to make one just black image of 3 by 3, I can use this formula, zeros of 0, 3 by 3. And if I want to have the one rectangle uh, from some dimension, I can do that, and then we can show this image there. Actually, after this, I should take the FFT, but like this, I feel that understanding the FFT and filtering is not suitable. Then at the later, I will tell you what we will do with this step. Then if we want to implement the FFT on the image, for computing the image, we should use the FFT2, and IFT2 can compute the inverse Fourier transform, and ABS can compute the Fourier spectrum, and angle can compute the phase angle. These are how we should implement this Fourier transform inside the MATLAB, and which function will help us to do that. Let us see some summary properties for the Fourier transform, which, as you know, we have the real part, Fourier transform, and symmetry of f mu. which you will see that we have in the general, there is the complex one, which is the conjugate. Symmetric one will have the relation between these. Then we have only real one, and we have only imaginary parts that you can see the relation between Fourier transform and symmetry of the F mu here in this table. That was one thing that we should do. But um, we have one function that we call it impulse function. Again, this you review in the math lectures. Impulse function, some people will call it Dirac because it's by the great work of the scientists that we know it as the Dirac, and they are considered as infinity high, infinity thin spike at the origin with total area 1 under the spike. It physically represents an idealized point mass or point 1. Okay. There is some definition for that. Definition 1 is that delta is 0 when t is not 0, and for the other case it's equal to 1. And definition 2 is that ft multiplied by Dirac is equal to f0. And there is nice concept in this impulse function, which shows that if you multiply that any function in the domain of time by changing of t minus t0, it will return it to the ft0, something like that, which cannot be computed using the normal integral methods. Impulse function, it has some equation like delta of x, which is the limit of 1 divided by a root square of pi and multiplied by exp part, which we call it the delta. Dirac delta function can be seen as the limit of sequence of zero centers normal distribution, as we show the figure here. Then the Fourier of the delta function is equal to 1. There is some proof for that. And similarity, we know that if we have the change in the axis between the t to t0, it can remain just some exp parts from that. Then Fourier transform of ft is equal to 1, as we say, and ejt is equal to ejat. Fourier transform of that will remain. These are the proof, which it's not our job, it's the mathematical part, just we'll go fast. Then purposefully for the sine and cosine waveform also I didn't give the proof. We can written the Fourier of the sine as with the form of delta or Dirac function, and cosine also we can write. The difference between these two terms is just this plus, as you can see. Okay. Then that was some background about Fourier. But why we should study the Fourier transform? Um, this is nice that observe the events in the frequency domain has some application. One can be denoising and phase-based image matching and directly manipulating the image in the frequency domain. These two applications help us or push us through the frequency domain, and especially for the Fourier transform job. Then we can make use of Fourier transform to compute the convolution efficiently, and FFT will help us as the good and effective box. The underlying theory is convolution theorem that we should know what is the Fourier transform. Let us review about very little about this convolution theorem that we remember in previous lecture that we talked that 1D continuous case, we know that f tau h of t minus tau, that d tau as the integration between minus infinity to plus. And convolution theorem said that the Fourier of the convolution is the pointwise product of Fourier transform, as it shows there. And then we can have these and travel between the time to the what we can say to the frequency domain with the convolution. What else we should know that we talked previously about the Gaussian filter, which we had before in the time or the x and y domain, we have the Gaussian formula. If we go for the frequency domain, we can change in up to this formula, which shows the Fourier transform of Gaussian function is also a Gaussian shell in the frequency domain. Then this Gaussian filter is a low-pass filter, which consider the first case. If fx is filtered by gx, means that the Gaussian formula. What will happen in the frequency domain is something like this, as I showed. Means that this is the fw and this is the gw that we have in the frequency domain. Now we review some parts. Let us do some experiment with the Matlab sides also to review some of the points that we have. Let me share my desktop screen with you that you can see it. Okay, can you see this Matlab environment, please? Oh, sorry, I think I mute all of you, sorry. Sorry. Can you please see?
Yes.
Yes,
Yes,
sir.
sir.
Okay, good. Then suppose I want first to do this smooth filtering on the Lena image. Generally, most of this filtering now we cannot do in the color image. We should prepare somehow to the binary or grayscale image, but here we can do. Let us see what should be the result of this filtering. You remember we had one formula there as the Gaussian filter. Here, there was some parameter that we call it sigma. Now, in this example, what I have done, I work with various sigma, sorry, delta, that it's there. See, we have between value of 2, value of 8, and value of 4, which is the smooth image I tried to do based on the original image part. Here, I use the Lena image and work with the Gaussian smoothing filter with the different sigma 2 to 8. You can go ahead and you will see that the image will become, we can say that it will gone, okay? Here in this example, we show the effect of the value of sigma on the image. Then what we can do now, if we want to have it with the 2D view for the Gaussian, what we should do? Because the previous one, just we worked with the 1D Gaussian filtering. Now let us do it with the 2D part, means that sigma of the y and sigma of the x, if I change them, how it will affect my image. Let me make it, yes, big. Now you will see. Suppose it's my original, then the sigma x is equal to 8 and sigma y is equal to 1. Sigma x is 1 and sigma y is equal to 4. You can see the result, little bit come below. Sigma 4 and sigma 1 I written there, sigma 1 and sigma y 8. It's the result that you can see after working with the formula of the Gaussian filters that we had. Then discrete Fourier transform, or DFT, which has the uh, sequence of endpoints, can be written with the F like this, and DFT also have endpoint. And finally, I can have the Fx, which is for the DFT. Uh, we have the formula like this. But for DFT, there is the fast algorithm that we call it FFT, or fast Fourier transform. And in the 2D form, we have two integration, which now depends on the x and y. Why we need two form? Because 2D form, because really our image are in the 2D formats. And then in the continuous case, we can use the integration, and in the discrete case, we are using the accommodation of the function, as you can see here. Some notes that you should uh, know in the DFT visualization I bring here, that for DFT, first is that the origin is not at the center of the matrix, and assume the original spectrum is divided into the 4 quadrants. The small gray field square in the corners represent the position of low frequency, as you can see here. And due to the symmetries of the spectrum of the quadrant position can be swapped diagonally, and low frequency locate appear in the middle of the image. I mean, the shifted spectrum can be something like this. Then for the visualization, we usually rearrange the DFT matrix to make its low frequency at the center of the rectangular, which is equal to fxy by -1 powered by x plus 1. And then it can be simplified, implemented by FFT shift function, which in that we will shift the zero frequency components to the center of the spectrum. And for the 2D or fast Fourier transform, we can use the FFT too. Then what we learned, that if we want to take the FFT or shift zero frequency, simply we can use these two functions and use it on the image. Then let us do one example on the image that and see the DFT on image part. Here what I have done, I am going to work on the cameraman example, which in that we will take the FFT, FFT log, and FFT shifted, and we will see the spectrum with FFT shifts and without that. Let us run this program. Yes. This is the spectrum with FFT shift without using that, and this is what we are using. Uh, what the difference is that you will see the low frequency are at the corner without FFT shift, and with FFT shift, the low frequency are at the center. Exactly the concept that we show, and it's implement simply with the Matlab, as you can see, and we saw actually before. Okay, let me close these windows and continue our talk. Then somehow there is the proof of this concept of shifted spectrum and original spectrum on this example number 3. In example number 4, I'm going to review the convolution of the 1D signal. Uh, as we review, I think we do this example. No need to again repeat it because it's not exactly with the aim of our topic, which is we should work on the image. But now you will see the convolution in the 1D can be like this, okay? But really what we need is the 2D, okay? Then we will put it aside and going for the 2D convolution part, which I'm again working on the Lena pictures and give you the example. As I tell you, today it's mainly review the Matlab's code on this filtering. And just initially, I give you some two parts I forget. Let me do it. Let us see what will happen at the end. Okay. Can you please see this formula? Can you see or not? The image, sorry.
Yes, sir.
Okay. What we have seen here, we have the original image and filtered one with the Gaussian filter that we studied. Then we have one motion filter and self convolution. Self convolution, it's happening like this here. And what we know about the Gaussian part is that the sigma value that they put a 5 and 5 here, it's there. And then with the motion filter also, they have done the other setting. If I want to tell you about this f spatial function, simply if we go to the MATLAB help, we can compare with the arrangement that we have done here. See, just 1 minute. Yes, we have the h size and sigma. Then sigma is 2 here and h size is 5. Then what about for the motion? For the motion, it's like this. We have the len and theta. Len is 10 and theta is 45. Okay, uh, this is the method that I want you to compare. Suppose if I put my sigma to 4, what should be the result? You will see that little bit it's become more blur. Or maybe I can do one thing. I can run this with the sigma of 2 and just this line. Not motion one, I need the Gaussian part. Let me add it here as one figure, new figure. And I put this as suppose 4. And I want to show you the sigma affection. The convolution with the motion filter with Gaussian here. Should put these 2. This one I should get again 2. Then I should show convolution with filter 2. And filter 2. And again, Gaussian filter 2. Yes. Now, let me see. There is no error. Yes. Now you can compare of these two images. Little bit it's become what we can say. Lord, let us make these suppose at 8. If you put 10, it should kill. Yes. See, now we can have the sequence of different. This sigma is not much more affected after this, but there is some different. I don't know. Can you see it on your computer proper? But something I saw that little bit it's become blurred. Anyway, this is one example, and whenever I will give you the code like this, I expected that you do some change and see the effect of them on the image. Then you will learn much more better from the other, what we can say, other example. That was one example that we have done, and I think here I made a mistake. This is again number 5, but this is the result of that. Okay, I should remove. Let us see then for the DFT. If I take I have this matrix with just one thing at the center, you will see that DFT of that can be these shapes, and DFT when it's rotate or other object is there, the center it's little bit something like that. The first image is have the rotation. This you should see, but basic step in DFT filtering, this is something that we can have here. Uh, we took it from page 121 of digital image processing. First, we should obtain the padding parameter which using the function pad size, and then obtain the Fourier transform for the image, then generate the filter function h the same size as the image, then multiply the transformed image by filter and obtain the real part of inverse FFT to G, and then crop the top left triangular like this. These rules I obey in my code that I show you, but no need for you to think. I think now let us have some break, and then we can come back as time is also little bit past. We are in the frequency domain filtering part, and we are reviewing some concept. Some of them we talked before, but not this much, we can say, deep. And also our main aim for today is reviewing the theoretical with some codes. Okay. Then filter of image in frequency domain can be something like that. First, we'll compute the FU and V of the image DFT, the secret Fourier transform of the image. Then we will multiply by a filter function of HU and V, and then we will compute the inverse DFT as the result, something like that. We have some pre-processing on our input image, then we will take the Fourier transform. Here, F, U, and V will come out. Then we will do the filter function on that, which will be multiplied by the h u and v. Then we will take the inverse function, and again post processing and enhanced image will come out. Um, then we can have some algorithm like this with suppose given image of f, x, and y, which have the size of m by n. We can set the p equal to 2m and q is equal to 2n. From the padded image, f, p, x, and y, which have the size of p by q, by appending the necessary number of zeros to f, x, and y, we can multiply this by uh, minus 1 power 1 x1 to the center is transform. Then we can compute the f u and v of f, p, x, and y. Then in the step number 5, we will generate the filter function of size of p and q, and we will get the modified Fourier transform of f u and v, which we multiply by h u and v, then obtain the proceed image and final result by extracting m and n region from the top left corner of j, p, x, and y. Um, little bit like this we can have. Actually, this is that Dr. Zhang image that he has done based on his image, this job, and then finally take the enhanced filtering from the input image that he took for us. Then what about for the convolution? For the convolution, we can given an image of x and y with a size of a by b and a special filter of h, x, and y, which has the size of the c by d, and we can set p is greater equal than a plus c minus 1 and q greater equal to b plus d minus 1. Then from the padded image of size p by q, we can appending the necessary number of zeros of x and y from the padded image filter of size p by q in the similar way. Then we can compute the DFT of f u and v and then h u and v of the filter. Then we can get the modified Fourier transform and obtain the processed image, then obtain the final result by extracting the central a by b region of G, P, X, and Y. Tips that you should know on filtering with the help of Fourier transform to implement the filtering in the special domain. Otherwise, you can filtering via the Fourier transform. In practice, when padding the image or filters, it's better to make it as the size with the power of 2, and the reiteration is based on the computer architecture. That was for the Fourier transform. Now let's go for the other type of the pass filtering, the low pass suppose filtering, which image smoothing actually in performing with the help of this filter. Edge and other sharp intensity transition, such as noise in an image, contribute significantly to the high frequency content of its Fourier transform. And three commonly used low pass filter we can have. One is that ideal low pass filter. One is that Butterworth low pass filter, and next is Gaussian low pass filter, which we'll go to see in the examples. But before that, little bit I will review the theory, not much more, very little. In the ideal low pass filter, it's like that. Simply, we will cut off the high frequency that are within the specified distance as d0. Means that after this d0, we will make everything 0 from the origin of the transform. It has some drawback or disadvantage like that. the filtering result have obvious ringing artifact, and ideal low filter is rarely will use in the practice. The transfer function for that can be something like that. If it's less than d0, the value is 1. Greater, it's 0. And where du and v is distance of u and v, give the du and v with this formula. Let us check the example number 6, not example number 7, because I think this counting is wrong here. I should make it, yes, I should make it 6 that you will not be confused later. Let us say one ideal filtering, because the size of program was big, I put it in this fashion, but you try not to do that. Which picture we work? We work with the uh, Lena. You can see the 2D inverse fast Fourier transform as well as the original image that we had, and you will see the effect of Fourier transform on that. How I have done that coding, it's like this. I put some comment for you that you can read, and from now we will going to have the same process for rest of this filtering. First we do the reading, then we will save the size of input image into M and N. Then Fourier transform we will take with FF2, as you remember. Some cutoff frequency we will take something like 13. Uh, you can suppose change it. Let me suppose change this cutoff as 10. And now see the result. You will see that the image is gone. As much as I increase this cutoff frequency, it should have the better view for us. But remember one thing, this cutoff frequency is not something that we can predict it now. Again, as I said, depend on your application. Suppose if I put it 50, it should have more visible, but we can say the effect of filter may be reduced. See, effect is less. Yes. Okay, let me come back to the main one, which is 30. Then we will take the designing filter, which we had, and then Matlab library, which return the 2D, and we have the mesh grid on that. Then we will take the regulation distance and comparing the cutoff frequency determined there, and then we take the FT of image multiplied by that filter that we have, and then the output will come out. This is the ideal low pass filter, and which as example we can uh, see there. That is the result, which belongs to number 6, and we already see it. Then what we saw that as we change this cutoff, see this cutoff frequency, as we go to the right side, then the effect of uh, this type of filter becomes the same. It's obvious. It's not some new things. Okay. Meanwhile, I will not talk more about this type of filter, but we have one type which we call it max and min uh, filter that I found maybe this code is interesting also for you to see. Which, based on that, you can find the minimum and maximum between the neighbors, and you can see the binary image, min filter and max filter, which are also used and applicable in the image processing world. And people can use it in various applications. Okay, I didn't give you the detail for min and max filtering. Uh, Maybe I will put for the task that you write what is min and max filtering at the end of to the task. I will give you. Kaya, please you remember me to put it in the task. Okay. I think Kaya is sleeping and he didn't receive my signal. Oh, Kaya is not here, huh? Okay, let me see. Am I audible from your side or no? Why nobody
Yes,
answer?
sir. Can you
Okay,
hear me,
then
sir?
yes, Kaya, then remind me to put this min and max filter on the assignment. Okay.
Okay, sir.
Okay, then this is the ideal low pass filter. Now we just I show you the result on the sample that we have. Let us review from the book also. Here we will show an image. It's Fourier spectrum at the series of ideal low pass filter, radius of 5, 50, and 30 and 80. As you will see, the difference are there. And 230 superimpose on top of that. You will see the result of this ideal low pass filter here. Original image, radius of 5, radius of 15, 13, 18, and 230, which it shows the result of this ideal filter on this sample image. Generally, you know that two images are more standard. I mean, Lena image and cameraman are the main one that we also will go to use. The next low pass filter was Butterworth, which it was proposed by the Stefan Butterworth. And filter order can change the shape of the Butterworth filter. Suppose for a high order value, the Butterworth filter approach the ideal filter, and for low order value, it's approach the Gaussian one. The transfer function of this low pass filter of order n with cutoff frequency of d0, it's something like this, as you can see. And this is the equation. This is the d0 as the cutoff, and smoothly it's going to cut. The difference between this and that ideal is that if you see the ideal one, on the d0, it's one straight line. But here there is some ramp for the this type of uh, image. Yes. Here, suppose you can see the butterworths on the image with again different radius of 5, 13, and 230, 80, and 15, as it shows. There is one more filter that in the low pass filter that we call it Gaussian low pass filter, which it has this transfer function, and the du and v here is the distance from center of frequency rectangle. You will see here also we have some smoothness than the ideal one, and again you can see the results here. And suppose for some low pass Gaussian filter, this example is very nice, which based on that you can see the connected broken text here. Suppose here some text was broken, as you can see that this filter can rectify. Now let us see based on the example about this filter that we review. Suppose yes, this one, which is the cameraman, and we are going to see the filter on that. Let us see. It may take little bit time. Even code is not big, but as my CPU is engaged with that, yes, it's come. Yes, you can see the filtered one as well as the original image here. Can you see, please? This is the
Yes, sir.
filtered one and this is the original one. Yes. The difference is that that here you will see even some convolution job that we have done on the image, and this is the effect of that type of filter. Let me close all, then the next time everything will go faster. The next is again ideal low pass filter, but now we will do it on cameraman. Let me first copy it, then we'll talk about the code activity. Yes, what we have done, again, we have the cutoff region. It's same as Lena, but now the figure is changed. Uh, you will see that the output is little bit, not little bit, it's corrupt, but it has the filter, it's not corrupt. And based on the application, later we can decide that this uh, output is desirable for us or no. Now, in this stage, we cannot say that which filter is good and which filter is bad. Okay, don't forget this point that now we don't know which one is proper. We should know the example, and then based on that, we can based on that we can take decision about it. Maybe you want to see more example on this part. Simply you can see, suppose, low pass filtering and see the effect of the Gaussian filters, which remove uh, you see this line near the eye is removed, and this is used, suppose, for photograph to publish, means that this filter is not bad. One application of that filtering should be this part. Okay, the next thing that we should review is about sharpening in frequency domain. You know that edge and fine detail in image are associated with the high frequency components. High pass filter only pass the high frequency, drops the low one, and high pass filter are precisely the reverse of low pass filter. Then we can have this formula: 1 minus low pass filter on the image can cause the high pass filter for us. Let us see the ideal high pass filter. Now we have the reverse job. If it's greater than d0, it's 1, and if it's less, everything is 0 there. Then let us check this. Now high pass filter on image and see the effect. Yes. This is the ideal high pass filter that we show the result here, but let us see what was the cutoff. Uh, yes, cutoff was 10. If I change the cutoff, suppose to 50, let us see the result. See, it will kill the image. Because what will happen before that 50, there is lots of information which may we need uh, to have the somehow visible, we can say, image. I cannot say it's good or bad. It depends on the application. Here it's again one more example with the different cutoff of 15, 13, and 80, as you will see with the one image as the sample. Low pass filter, we have butterworth of the high pass filter, which from this part means that this cutoff again we can go smoothly to the image. Here is the example of this butterworth high pass filter. Let us run the program. Yes, this is the butterworth high pass filter. As you will see, from the edge side, it's become more shiny. The next part is this butterworth on the same photo that we had with the different cutoff of 15. Then the next was 13, and the last is 80 as the cutoff frequency that you can see here, an effect on the image that we have. Then as low pass filter, we have the Gaussian part. In high pass filter also, we have the Gaussian pass filter, which it has this formula, and D is the cutoff distance as before. You will see that how it will affect. As much as smooth, we can touch the cutoff part. You can see that the filtering jobs is much more, we can say maybe better. That is why we have the different type of filtering. Let us test the ideal high pass filter with the Gaussian part. Let me see the result of that. So I think we test this. Sorry. Okay, this is the Gaussian now high pass filter with 15, 13, and 80 again setting, as you will see. Okay, now let's go for the FFT part. Now we'll go for the FFT part, which is the reason that Fourier-based technique have become so popular is the development of FFT, which this FFT allows to be carried out in the reasonable amount of the time. The first thing, as even you saw, it takes some times for me to process the image, but in FFT, it can do it faster and also reduces the amount of the time required to perform the Fourier transform by a factor of 100 to 600 times. And suppose if I want to take FFT of my cameraman in Matlab, cameraman example, let me see what we can do here. Let's go ahead. First, I should do the reading. Then I should take the FFT2, and then we should take the log2, and then absolute value of the L as the log1, and then this is my FFT of my image. Which data, which information we can take now is depend on the application that we have. Little bit to the end, we can say that Fourier domain filtering and special domain filtering, there are some similar jobs that we can do in these two domains. But filtering in the special domain can be easier to understand, but in frequency can be much be faster, especially for the large image. In summary, we talk about the image filtering in the frequency domain. We talk about the background. We talk about the uh, Fourier series to the Fourier transform. We talk about properties of Fourier transform, discrete Fourier transform, basic of filtering, smoothing, and sharpening using the frequency filtering part. Uh, that was the talk that I bring and some reference that we speak for today lecture. But because we have time, maybe we can talk on 2, 3 more sample of program, and also maybe we can review them better that I have this example. Now, any question till now?
No, sir.
Okay. Just let me see that can we take the FFT with this code also? Okay, I want to take FFT and absolute value of the cameraman pictures. Let's see, can I take or no? It should be the result. This is the cameraman, then the apps value is something like this. And real and imaginary part, it's something like this. Okay, we can take the FFT of that. Maybe then we can add it inside of our code. Let me also share the image part. DFT of image. I will put the name for that. The next part, maybe can add to the previous. Yes, suppose this is the absolute value of f that we can have. It's something like dark page, and maybe it's not uh, but because the filter that we take is 256, as you can see here. and this is the other thing. No need for them. Okay, well, I think it's okay for reviewing the filtering, especially for the frequency domain.